A particle is projected from a point on a horizontal plane at 30 degrees above the horizontal and with an initial speed of 50 meters per second. The particle will experience constant downward acceleration due to the Earth's gravitational pull of 9.8 meters per second squared. We want to calculate the equation of the trajectory. So, if we have the particle being projected like so, we know this is 50 and this is 30 degrees. Resolving the velocity means that along here we get 50 cos 30, and up this way we get 50 sine 30. Now we know sine 30 is a half, so this is equal to 25, and we know that cos 30 is root 3 over 2, so this is 25 root 3. The acceleration is vertical. So with no horizontal acceleration, the distance travelled in this direction would be 25 root 3 t. Vertically we have this acceleration, which is downwards, so we can use ut plus a half at squared. So that's going to be 25t, take away half of 9.8, 4.9 t squared. This one here tells me that t is equal to x divided by 25 root 3, and of course to get the equation of the trajectory we want to eliminate t, so we'll substitute this into here, and y is going to be 25 x over 25 root 3, take away 4.9 x over 25 root 3 squared. So 25's cancel here, so y is going to be x over root 3, take away 4.9 x squared over 3 times 25 squared. 25 squared is 625. Multiply that by 3 is 1875. We now want the time of flight, so that means the length of time until the particle comes back to the horizontal surface. In other words, when y is 0. So we want y is 0, and that means that 25t take away 4.9 t squared is equal to 0. So t into 25 take away 4.9 t equals 0. Obviously this t gives us t equals 0, and the other t gives us 25 over 4.9. So I might go to standard. 25 divided by 4.9 gives me 250 over 49, and that would be the time of flight, and of course we can get that as a decimal easily enough by doing this. The range will be the distance here, so we know that x is 25 root 3t, and it lands at this time, so that's going to be 25 root 3 times 250 over 49. And so we're going to do the previous answer multiplied by 25 multiplied by root 3. And probably best to get that as a decimal. So 220.9 meters to 1 decimal place. We now want the greatest height reached. Now if we think about the velocity in the y direction, we can get that by differentiating this. So that's going to be 25 take away 9.8 t. Of course we could have used v equals u plus at as well. So at the greatest height the vertical velocity is 0, so t is going to be 25 divided by 9.8. If we substitute that back into here, that will give us the greatest height. So So that's 25 times 25 over 9.8. Take away 4.9 times 25 over 9.8 squared. Let's see what that comes to. So we have 25 times 25 divided by 9.8. Take away 4.9 multiplied by 25 over 9.8 squared. That gives us 31.9 meters to 1 decimal place. We now want the position vector, which is easy because we have x and y already, so that's just going to be 25 root 3 t, and 25t take away 4.9 t squared. And then we want the distance from the origin 1 second after launch, so r of 1 is going to be 25 root 3, and then we'll have 25 take away 4.9, which is 20.1. And so what we want is the square root of 25 root 3 all squared, add 20.1 squared. So that's the square root of 25 root 3 squared, add 20.1 squared, and that's 47.7 meters